Welcome everyone to today's session on novel imaging acquisition methods. And let me also begin by acknowledging the traditional owners of the land on which we meet today, which are the Turrbal and the Jagera people, and pay my respects to the elders past, present, and emerging. My name is Saskia Baumann. I'm from the University of Queensland, so I'm a local, and my co-chair is Jean Chen, and I'll hand over to her to introduce our first speaker.
Okay, thank you, Saskia. So our first speaker will be Kiana Kothe, and she will be speaking about the evidence of neuroinflammation and excitotoxicity in CFS using single-voxel MRS.
Hello, good morning. First, I want to thank OHBM and the chairs of this session for inviting me to talk. And before I start, I also want to acknowledge the traditional owners of the land on which we gather and pay my respects to elders past, present, and emerging. My name is Kiana Kothe, and I just finished my first year of my PhD at the University of the Sunshine Coast Thompson Institute. My supervisor is Professor Zach Chan, and I'm very excited to provide some preliminary evidence of neuroinflammation and excitotoxicity in myalgic encephalomyelitis, also called chronic fatigue syndrome, using single-voxel MRS. I have no disclosures. Before I start, I want you to imagine waking up every day and feeling like you've just run a marathon. For people living with ME/CFS, simple daily activities like reading, standing, or even thinking can lead to an overwhelming crash, which makes regular day-to-day life activities extremely difficult. ME/CFS is characterized by heterogeneous symptoms such as chronic fatigue, pain, unrefreshing sleep, autonomic dysfunction, and/or impaired cognition. And it affects around 0.89% worldwide. Despite affecting millions, this research has remained misunderstood, underdiagnosed, and under-researched. However, a popular hypothesis currently is that of neuroinflammation. One problem with this, though, is the methodology in order to assess neuroinflammation is rather invasive or just not feasible. An alternative option could be magnetic resonance spectroscopy by measuring neurometabolites that are a reflection of neuroinflammation. As the first part of my PhD project, I wanted to investigate the group differences of neurometabolites indicative of neuroinflammation using single-voxel MRS. And most specifically, we were interested in these 5 metabolites. So GLX, which is a combination of glutamate and glutamine and reflects excitotoxicity. Myoinositol, which is a glial marker in vivo. Lactate, which is involved in the modulation of immune responses. Total N-acetyl-aspartate, which is a neuronal integrity marker. And total choline, which reflects membrane turnover. Overall, we hypothesized increases in the first 3 and decreases in total N-acetyl-aspartate and total choline. Additionally, we assumed that the metabolites might correlate with symptom severity. Before our participants get to go on the scanner, we have several assessments they have to undergo through in order to assess comorbid symptomatology, fatigue states, and covariates. After the scanning session, we assess fatigue states again. And in the scanner, participants undergo several sequences, including a functional MRI sequence, where they perform this task. This task is a symbol-digit matching task, which assesses processing speed. What they basically have to do is decide if the digit and the symbol on the bottom matches the reference above. On the console, we then fit the results in real time using bold signal changes associated with the task. And for that, we're using a functional localizer to guide the placement of the voxel of interest per participant. Unlike structural MRI, MRS provides biochemical information, so we can basically construct a chemical fingerprint of the brain. We're collecting MRS data from our tailored voxel, which looks something like this. So we have a linear combination modeling that is used in order to model the spectrum, and we can this way investigate the different peaks that we're interested in. The most common MRS method is single-voxel MRS, and we used exactly that, with our voxel being placed in the DLPFC with a size of 27 × 20 × 12 millimeters. We also used an unedited single-voxel press sequence with an echo time of 33 milliseconds, and for that we needed to create a tailored basis set file. In total, we collected 200 acquisitions. Following visual inspection of model fit and evaluation of quality metrics, we included 100 participants in our analysis. 52 of those were healthy controls, and 48 were participants with ME/CFS. For our analysis, we ran several ANCOVAs controlling for age, sex, BMI, and activity levels. And there were no significant differences between the groups, so our group was pretty well matched. Additionally, we also included depression and anxiety symptomatology, as participants with ME/CFS are scoring higher in these regards, and they might also affect metabolite levels. Data processing and metabolite fitting were performed using the Osprey pipeline, which used also a linear combination pipeline, and total creatine was used as the internal reference for metabolite quantification. Now onto my results. After running our ANCOVAs, we found significant results for GLX and total choline, providing partial support for my first hypotheses. I also plotted these. In blue, you can see the results for participants with ME/CFS, so we can see an elevation in GLX and lower scores in total choline. No significant differences were found for the other 3 metabolites. However, we can note some covariate effects, particularly for sex, age, and physical activity. Next, following on to hypothesis 3, I investigated the differences between groups in fatigue state, which were assessed before and after the scanning. Overall, fatigue increased over time for both groups. However, participants with ME/CFS had higher baselines than healthy controls, and also their fatigue increased significantly more than that of healthy controls. So all predictors were significant. But we didn't find significant correlations between the metabolites and fatigue state changes. So, my conclusions. While significance was not observed across all 5 metabolites, the 2 that were significant still suggest a link to neuroinflammation. This provides partial support for my first 2 hypotheses, with lower levels in total choline and ME/CFS potentially reflecting reduced membrane turnover, which indicates impaired cellular repair or glial membrane dynamics. Additionally, elevated GLX suggests increased glutamatergic activity. As glutamate is the major excitatory neurotransmitter in the brain, this can have widespread effects. Not only can it trigger an influx of CA2+ into the cell and consequent excitotoxic cascades, it also leads to interlinked mechanisms such as mitochondrial dysfunction, increased oxidative stress, which have both been proposed in ME/CFS. What we're measuring with neurochemistry here can give us hints at what is at play behind the scenes. For example, impaired glial glutamate interactions, as well as interactions with pro-inflammatory cytokines. Regarding my third hypothesis, we found that symptoms such as fatigue worsened during the task-based scans, but we could not find significant associations between fatigue changes and metabolites. Our results evaluated the metabolites in a static way. However, the story around our MRS sequence is a little bit more complicated than what I led on earlier. The task that I mentioned previously during the functional MRI sequence, this task is performed a second time during the MRS sequence, which provides us with functional MRS data with multiple alternating rest and task blocks. In addition, we interleaved a water reference, or a T2 star, which could be of interest if you want to correct for line width changes and look at both signal amplitudes across the blocks. The water reference you can see in red and the metabolite scans in blue. Overall, we're looking at an average spectra across both tasks and rest periods, which may have masked potential functional effects. So the next thing we want to investigate and understand are the dynamic neurochemical aspects over time in populations that may fatigue differently. And for that, we need to disentangle cognitive task engagement from rest, and they might be especially interested looking at metabolites such as GLX. In order to do this, it would be good to refine the extraction of this embedded water reference, which has proven a little bit difficult so far with regular tools like FSL-MRS or Osprey and even LC model. So I welcome and appreciate all your thoughts, questions, and suggestions you may have. My postal number is 1951, and I'm happy to discuss any ideas you may have to help guide and refine the next stage of analysis. I want to thank Dr. Jacob Levenstein, who I worked with closely for this project, my research team, my supervisor, all the participants who have supported this project with their time and enthusiasm, and also you for your attention. Thank you.
Thank you very much. We have 2 minutes for questions. Anyone from the audience? And please, if you want to also submit your questions online.
Sorry, just a quick question. So in your functional MRS experiment, I was just wondering, what is the role of the T2 imaging in your interval for your functional blocks?
Yes, so it's quite an unusual sequence. Usually you have the water reference or the T2 separate. In this scenario, it could be good to look at, for example, line width changes, which represents noise. So if you want to account for different noise levels across the blocks, this would be useful. Yeah, it's also basically modeled from a functional MRI sequence, so that's probably why it was designed that way. For this analysis that I want to do, it would be great to disentangle them, but ideally it would be for noise correction.
Thank you.
Yes, thank you.
Interesting talk, thank you. I'm curious about the specificity of these neurochemical signatures for inflammation and what other things could be going on.
Yes, that's a great question. I think I try to hint towards that, that it would be ideal to find this chemical fingerprint with all the metabolites that would give us a more conclusive idea what's happening behind the scenes. Overall, these metabolites are indicators of mechanisms, but there's still so much at play that might be useful to research further, like glial cell increase or inflammatory cytokines. So it's probably good to get a bigger picture and an idea what's happening, but in order to be really, really specific, we need to find other ways as well to complement that with my results, for example.
Thanks.
Okay, sorry, we have to move on in consideration of the time. Please come up after the talk to get your questions in. Thank you again, Kiana.